Any questions?
Arsene, I have a quick question for Brianna. This is Calvio Duga.
Hello.
Hi. I think I missed something. At the beginning, you seemed to imply that the data sets that these folks picked were different primarily because they seemed to be in different states, i.e. they were one was highly variable in terms of luminosity and the other one wasn't. And then when you refit everything, you are now saying that's actually more the mass and the distance and the inclination which is maybe the source of the problem. Have I got this? Am I confusing things here?
So both of the groups claim that they have disk-dominated spectra.
Yeah.
So one possibility, so the distance and mass and inclination all changing definitely push the spin up. But it's also possible that the reason why we can't get fits to the McClintock et al. Data is possibly because that it's not actually disk-dominated. It could have a lot of contribution from the corona in these sources. And so that's also a possibility. But yeah, if that makes sense.
Thank you.
Mm-hmm.
Thanks again for nice talk. And let's now move on to the next all-time favorite source, Hercules X1. Dennis Leahy will tell us about new long cycles.
You have sound and video?
We
have seen coming. Yes, now it's there.
Can you see it now?
Yes, please take.
Okay, great. Right. So this is about just an analysis of the monitoring data over the past. The monitoring data is over the past 15 years, but the analysis has just been done recently, done with my graduate student, Julia Wang, mainly. That's sort of a brief review. I think everyone is familiar with Hercules X1 with an intermediate mass companion, A7 type star, about 2.5 solar masses. And the topic of interest today is the properties of the 35-day cycle. And one thing to keep in mind is we have very accurate orbital parameters, but the inclination is moderately well constrained. It's about 85 degrees, but that might be plus or minus 2 or 3 degrees, which prevents accurate mass measurement of the neutron star. Okay, that's not what I'm concerned with here. Now, the 35-day cycle has been observed for many years. Here I show the RXT ASM light curve that was made in 2002, showing the main high state and the short high state, and then the two low states. And we're all aware of the disk occultation model. It works very well where the high state is dominated by X-rays from the neutron star. The short high state also has an important contribution in the early part from the neutron star. Scattered X-rays make a bigger contribution to the short high state than the main high state, but it's they're in there in both of them, which could be seen in the pulse shapes as well as the light curves. So what is new here is we've constructed new 35-day average light curves using the ASM data, but now right to the end of the mission, plus also the Swift-BAT monitoring data. So here in red is shown the Swift-BAT light curve, and in blue the RxD-ASM light curve. And I'll just mention that this was how we create the average late 35-day cycle, because the, well, I'll mention that a little bit later because I wanted to say a couple other things first. Okay, so other things related to just verifying this twisted, tilted precessing accretion disk model. There's been a long, well, since the discovery of Hercules X1, we've known of the optical light curve changes 35-day phase, and that can be fit. Simple models were used, but now we have better models that could fit the changing optical light curve with 35-day phase. Is basically the face of the companion star, and the precessing disk, the shadow of the disk, which is just indicated by this band here along the equator, moves with time, so that the and the beat period between the 35-day precession of the disk and 1.7 day orbital period is the 1.62 day period you see in many things, including the optical, but the shape of these light curves can be produced by that. Okay, so here's just a schematic of the accretion disk and a schematic of how the accretion disk causes the 35-day flux cycle. So if you think of the neutron star in the center and the observer moving along this line, the observer can see the neutron star when the disk doesn't block it here during main high and during short high, but it could also see scattered X-rays beyond the point where the edges of the disk block the line of sight. Okay, and the further evidence which I mentioned earlier on the disk occultation model is the modeling of the pulse shape changes, which occur regularly over a 35-day cycle. This has been out for a long time. And something more recent from this Rudiger Starwick and his group, he was measuring the turn-on times of the 35-day cycle from flux, from the light curve, and comparing it with turn-ons determined by the changes in pulse shape, and find they agree, which basically confirms the disk occultation model and rules out any neutron star precession. Okay, so for the current analysis, working with the ASM data and the BAT data, here's a typical sample of ASM data, which is quite noisy. And the BAT data, although we don't have the error bars here, it's not quite as noisy as ASM. So it's a challenge to determine when the cycles start and stop exactly. So what we did is remove all the eclipse data and use a cross-correlation analysis with a template. And the initial template was taken as the old published 35-day average light curve. And then after the cross-correlation analysis is done, you could line up all the data and create a new template, and you iterate that until it converges. So this just shows the BAT light curve again, after including basically all 14 years of the BAT data. We have a similar thing for the ASM light curve. Here are the cycle lengths. The average cycle length, 34.79 days. There are large excursions, but the average variation is only a little over a day. And we find no secular change of the 35-day cycle over the roughly 14-year period. This just shows a histogram of the times. Down here, we also show standard deviation per bin. So this is the average light curve, and then you compare each individual sample from SWIFT-BAT, and we see that the largest variations happen during short high, which can be, it has to be still interpreted yet. Okay, so this is sort of a summary again, but now adding the MAXI data. So MAXI actually has quite good sensitivity, well, comparable to BAT. Here shown both the MAXI data in red and the BAT data in blue. And you can clearly see the eclipses in both data sets, and you can see some dips also in some of them with the main high and short high. But again, the noise dominates over the cycle. So we take the multi-year average and do a cross correlation analysis on both sets again to get the two light curves. So here's the Swift light curve, or the BAT light curve in red, and the Maxi one in blue. And the interesting thing is that when we do this, we could see regular, looks like dips in the softer X-rays, the 2 to 20 keV compared to the 15 to 15 keV. This first dip is actually the turn on, so that the whole system turns on earlier at the higher energy X-rays. That's just due to absorption of X-rays by the outer disk edge. Same with short high, turn on is earlier in the hard X-rays, but we also see these dips. I'll say something more briefly about that. One other thing we've done is we looked at the orbital phases of the peak. Because we're using a cross correlation analysis, we're actually measuring the time of the peak of the, it's actually the time of the overall phasing of the whole light curve to the individual data sets. So we take the average light curve and we get the best phasing compared to the overall data. And that's more sensitive to the bright part than just the turn on, although the turn on is important too. So we're fitting the whole light curve to get this. It's not just turn on, but the orbital phases of peak in both BAT and Maxi, so a flat distribution with a peak around 0.5. This is not easy to explain, so we think that's just a selection effect because eclipses will bias when you do this. And I think the bias of the eclipses on, well, we threw away the eclipses, yes, but the data is lower because of the, when I'll show you the orbital light curves, so you'll see that the orbital light curves peak around orbital phase 0.5. But the same bias effect occurs when you look at individual data sets and turn-ons. So there's no way, I think we just don't have a method of measuring orbital phases of turn-ons yet, except for the high sensitivity observations with the RxT PCA and other instruments. But over the whole history of Hercules X1, there's only been about half a dozen turn-ons observed, not enough to do a statistical study. Okay, continuing, with these light curves here, now we have better measurement of the different phases than previously. So I just list them here, but you won't go through them. So we know the when the different phases start and stop better than previously. Another thing that came out of this, here's the Maxi 2 to 20 keV light curve. We also have good measurement of the softness ratio. Basically 2 to 10 keV Maxi is the best band to use in terms of noise. And then for the high energies, the BAT 15 to 50. So the softness ratio is the red curve. And during main high, we have small errors. When you get in low state, the errors are too large. And again, during short high, we have fairly reasonable error bars. So we could measure, basically we could model a column density going into turn on and during short high and see this column density going up and down. Same with main high, drop of column density at turn on, and then these dips that seem to occur at the same phases. Okay, last topic, which I'm going to discuss about is how the orbital light curves change with 35-day phase. So during main high, here's the main high orbital phase light curve, which typically shows a big dip at the end beyond orbital phase 0.7. So this is Maxi, or BAT, the highest energy where the dip is weakest, and then the 10 to 20 keV Maxi, the 4 to 10 and 2 to 4 keV Maxi here, which show stronger effects of absorption. Okay, so the typical orbital light curve is only flat during main high. During short high, during turn on, short high, and the two low states, the light curve is a lot noisier, but it doesn't have this nice shape that it does during main high. And one thing we've done is we've confirmed that by comparing the light curve during low states with the optical light curve during low states, that there's an offset in phase, which is not surprising because the X-rays are not just coming from the companion, they're also coming from a larger scattering region. But that I won't show the details of that. What I wanted to say something about was more about how the orbital light curve changes as a function of 35-day phase during main high. So we've taken that main high one. I've only got a minute left and then I'll end. So this main high, we break it up into 5 different pieces. So this is early part of main high, peak of main high, and then decline of main high. And we could see this, there's a late dip, which with time becomes less deep and marches to earlier orbital phase. That's the normal marching dips phenomena, which is known, but we also see this early dip, which only appears during basically early main high and turn on to main high, and then it disappears. So there's 2 different types of dips. There's the marching dips, which are well known, which we measure here. So the orbital phase gets earlier and the depth of the dip decreases, so it gets shallower. And one thing else we've noticed, which is suspected but better measured now, is there's significant scattering or blockage going on because the dips here are consistent not with, this is modeling the 5 bands. So this is the column density, and we have basically a blockage factor or scattering factor. So there's loss at high energy where the photoelectric absorption is not important, which is related to the shape of the disk. Okay, I'm done there. I'll just leave my summary up because I'm over time now. Thank you.
Thank you, Dennis. Any questions? Yes, Demos.
Yes. When it's in the low state, you said there's some scattering that comes, radiation that comes to your line of sight. Is there any indication of spectral features or any indication of what is the total column of that?
Yeah, actually, with my PhD student back in 2015, we looked at the RXT spectra for one observation of low state and short high, and there we could verify part of the X-rays came from reflection off the companion, and then the rest we just took as scattering. Scattering is really hard to determine where it's coming from because it doesn't have any spectral signature. Basically, at those energies, you're just doing Thompson scattering. So
I see. Okay.
But the reflection.
So what would be the column, the Thomson depth of that component?
It's quite high. I'm trying to remember. I think it's about 5 times 10 to the 23 or 10 to the 24.
I see. That's interesting. Yes.
But if this at 15 to 50 kV in BAT, even at a few times 10 to the 23, if this was purely absorption, we wouldn't see this. So there has to be, see these dips here where it's going below 1. It's definitely not photoelectric absorption. Yeah, because the cross section's not high enough at 15 to 50 keV.
So
it's
there
way
is
below
some
the top.
large scale gas with column of a few times 10 to 23 that basically scatters something into your line of sight.
Yeah, well, we're hoping to be able to detect some scattering off the accretion stream, but I think it's just too small in angular size.
Okay, thank you very much.
Is there a long-term optical monitoring that can show somehow in optical whether similar patterns are present?
Yeah, actually, there's been a couple of papers. Gee, I have them on my presentation, which I just closed. There's Voloshina has been doing it, as well as the British group. This is Martin. I think this is working with Martin Still. It's from 2011, but yeah, I think we could still make progress by doing more detailed modeling of this. And one data set that I have is recent FUV observations with UVID instrument and AstroSat, which look very much like this, and can be used to actually constrain the disk shape.
Very interesting. Thanks a lot.